The measure of distance between worlds begins with the clocks and speeds that already structure life on Earth, because the limits of human travel are easiest to see when the starting scale is steady and familiar. Human time is built from Earth's rotation and orbit. A day follows the turn of the planet. A year follows the path around the sun. These cycles are not only cultural, they are physical references that remain stable enough to support navigation planning and measurement. When travel is described in human time, it is described in days, months, and years, because these units connect distance to lived schedules and to the endurance of people and machines. Human travel also begins with everyday speeds. A person walking covers a few kilometers in an hour. A bicycle covers more. A car on a highway covers tens of kilometers in an hour. A train can cover hundreds of kilometers in an hour. An airplane crosses continents in hours, moving close to 1,000 kilometers per hour. These numbers are not important for their exact values. They're important because they set the meaning of far in daily life. A journey of a few hundred kilometers can be done in a day. A journey of a few thousand kilometers can be done in a day by air. A journey around Earth is possible within a day at high speed. In this range, distance is large but manageable, and time remains a practical tool rather than a barrier. The moment distance between worlds enters the discussion, the role of speed changes. Space does not offer roads, and it does not offer air for lift. Motion is governed by momentum and by gravity. The first step outward from Earth shows this change clearly. A spacecraft must reach orbit, meaning it must move fast enough that as it falls toward Earth, it continually misses the surface. This orbital speed is many times faster than airplanes. It is measured in kilometers per second rather than kilometers per hour. The leap from 1,000 kilometers per hour to several kilometers per second is a leap of an order of magnitude in speed. Yet in space, even such speeds quickly meet distances that turn minutes into hours and hours into days. Human intuition about travel built on the surface of one planet begins to strain. Human time remains the same. A day is still a day. A year is still a year. What changes is how much space can be crossed within those units under known propulsion and under the constraints of energy. To describe the limits of human travel, it is useful to separate three related but distinct measures of time. The first is travel duration, the time required to move from one place to another. The second is communication delay, the time required for information to travel between those places at the speed of light. The third is mission duration, the total time a journey and its operations require, including preparation travel and the work performed at the destination. The limits are not the same for all three. A robotic spacecraft can tolerate long travel durations and can operate with long communication delays by using autonomy and pre-planned sequences. Human travelers require life support and shielding and must manage risk, which makes long travel durations more difficult. Communication delay affects both because it limits how quickly help and guidance can move between Earth and a distant crew. Mission duration matters because it defines how long systems must remain reliable and how long a crew must remain healthy and supplied. In this first section, the aim is to establish human time as a scale that can hold these measures without decoration. The distance between worlds is first expressed as a question of how many days pass, how many months pass, how many years pass, and how long it takes for a signal to cross the gap. Even before numbers are applied to specific destinations, the basic structure of the problem is present. Space travel is not only faster movement, it is movement under strict energy budgets through environments that do not support human life, toward targets that are moving in their own orbits. A simple everyday measure can show how quickly the scale grows. A car traveling 100 kilometers in an hour covers 2,400 kilometers in a day. That is a meaningful distance on Earth. In space, the Moon is nearly 400,000 kilometers away. At car speed that would take more than 150 days in a straight line, and a car cannot travel in vacuum. A spacecraft reaches the moon in a few days because it travels far faster than a car, and because it follows a trajectory shaped by gravity. This difference shows the first boundary between daily human travel and interworld travel. The moon is close in cosmic terms, but far enough that the trip is not an extension of ordinary transport. It requires a launch, a trajectory and systems that operate outside Earth's atmosphere. It is still close enough that communication delay is only a little more than a second, so human control can remain nearly immediate, and emergencies can still be addressed with relatively quick decision cycles. Even so, the travel time is days, not hours, and the mission requires careful planning. This is the outer edge of the near-Earth region. From there, the distances to other worlds grow rapidly. The inner planets are tens to hundreds of millions of kilometers away depending on orbital alignment. The outer planets are hundreds of millions to billions of kilometers away. At these scales, travel times become months and years for a robotic spacecraft, and the communication delay becomes minutes and then more than an hour. Human time begins to stretch. A mission to Mars, even on efficient routes, typically involves many months of travel. A mission to Jupiter or Saturn involves years. These are not claims about what is desirable. They're consequences of orbital mechanics and propulsion. A spacecraft must move from one orbit around the Sun to another. The Sun's gravity sets the natural speed and timing of these transfers. To make them faster requires more energy, and energy is limited by propulsion and mass. The limit of human travel is therefore not only a question of willingness, it is a question of energy per unit mass of life support mass, and of how long systems can operate without resupply. Human time also provides a way to connect distance to life. A journey that takes days can fit inside the rhythm of work, weeks and short-term planning. A journey that takes months begins to require sustained support and increases the consequences of delay. A journey that takes years becomes a long-term commitment. For humans, years in transit mean prolonged exposure to radiation beyond Earth's magnetic protection, prolonged exposure to microgravity or partial gravity, and prolonged reliance on closed-loop life support. These risks increase with time not because time itself is dangerous, but because the environment is hostile and because small failures can accumulate. For robotic systems, years in transit mean power must remain available, thermal control must remain stable, and components must survive radiation and aging. These are also time-linked constraints. The limits of human travel are therefore best described as layered limits that become active at different timescales. Some limits appear immediately, such as the need for vacuum-compatible systems and the need to reach orbital speed. Other limits appear over months, such as the need for reliable life support and the cumulative effects of radiation. Still others appear over years, such as system aging and the social and logistical challenge of maintaining a mission. Beyond the solar system, distances become so large that travel times at known speeds become centuries or longer, and the concept of a single mission operated by one generation becomes difficult. In that regime, human time becomes lifetime time, and the word limit takes on a clear operational meaning. This section does not yet move to those distances. It establishes the stable base. Human time is a day, a month, a year. Human travel is measured in speeds that begin on Earth, and then climb into kilometers per second for spaceflight. The limits of human travel will be revealed by translating distances between worlds into these time units, and by observing when the required time grows beyond what body systems and institutions can sustain. The next step is to place the nearby worlds in a moving solar system map, because without understanding orbits and changing geometry, distance and time between worlds cannot be stated honestly or consistently. The distance between worlds cannot be described as a single fixed set of numbers, because the worlds themselves are in motion. Earth is not stationary. The Moon orbits Earth. Earth orbits the Sun. The other planets orbit the Sun as well, each on its own track with its own pace. The outer region here is the solar system map as a moving system, because the limits of human travel depend not only on how far destinations are, but on when they are far and when they are nearer, and on how gravity shapes the routes between them. The solar system is organized around the Sun, which holds most of the mass, and therefore dominates the gravitational environment for interplanetary travel. The planets move on orbits that lie close to the same plane and are close to circular but slightly elliptical. Each orbit has a period the time to complete one revolution. Inner planets orbit faster. Outer planets orbit more slowly. This pattern is a direct result of the Sun's gravity, and the way orbital speed depends on distance. From Earth, these motions appear as changing positions of planets in the sky, but for travel they are changing distances and changing target locations that must be met at the right time. The nearest world is the Moon. Its average distance is measured in hundreds of thousands of kilometers, and its orbit around Earth takes about a month. Because the Moon is close, the distance does not vary by huge factors, and travel times of a few days remain typical for high-energy lunar transfers. The Moon is also close enough that communication delay is about a second, which keeps Earth and lunar missions tightly linked in operational time. The Moon therefore defines a near-world regime, days of travel, seconds of signal delay. This regime is still within the scale where human crews can travel, work and return without confronting years of exposure to deep space. Beyond the Moon, the next worlds are the planets, and here the geometry becomes more complex. The planets are not lined up at fixed intervals. They move, and Earth's distance to each planet changes continuously. A journey to Mars is not a journey to a fixed point. Mars is a moving target on an orbit outside Earth's. Sometimes Mars is relatively close to Earth, and sometimes it is far on the other side of the Sun. The same is true for Venus, which orbits inside Earth's orbit. The distance between Earth and Venus varies as the planets move, and the direction to Venus changes as well. This means that travel is planned around windows when the geometry supports a reasonable route. For Mars, a commonly used route is an energy-efficient transfer that takes advantage of orbital timing, and launch opportunities occur on a cadence of a little more than 2 years. This cadence is not a rule of mission policy. It is a consequence of how often Earth and Mars return to a similar alignment. In human time, this means that interplanetary travel is scheduled by celestial mechanics. A mission that is not ready when the window opens may need to wait many months for the next. For human travelers, this matters because it shapes total mission duration and emergency return options. The map of the solar system can be described as rings of distance measured from the Sun. Earth orbits at one astronomical unit. Venus orbits closer, Mars orbits farther. The asteroid belt lies beyond Mars. Jupiter is much farther out. Saturn is farther still. Uranus and Neptune are at greater distances still. Each step outward increases the scale. The inner planets are separated by tens of millions of kilometers at close approaches and more at far alignments. The outer planets are separated by hundreds of millions and billions of kilometers. Yet the travel problem is not simply to cross a gap. It is to move from one solar orbit to another. A spacecraft leaving Earth is already moving around the Sun at Earth's orbital speed. It must change its orbit around the Sun to intersect the destination's orbit at the moment the destination is there. This is why the road analogy fails. There is no fixed road length. There is a set of moving orbits and a set of possible transfer trajectories between them. Gravity provides the rule that links these. In a Sun-dominated field, a spacecraft follows an orbit unless thrust is applied. A transfer to another planet is therefore an insertion into a new orbit, then coasting, then a meeting. The time required is tied to the size and shape of the transfer orbit. This is why distances between worlds translate into months and years rather than days once the mission leaves the Earth-Moon system. The moving map also includes the fact that different destinations impose different requirements at arrival. To reach a planet by flyby, the spacecraft only needs to pass near it. To reach it in the sense of orbiting it, the spacecraft must slow down relative to it. To reach it in the sense of landing, the spacecraft must slow down much more and interact with an atmosphere or a surface. Each of these definitions changes the meaning of distance and time. A flyby can be achieved with higher arrival speed and often with shorter travel time. Orbit insertion and landing impose energy reduction requirements that can favour longer transfers or greater propellant loads. For humans, landing and return add further constraints. A crewed mission is not only an outbound route, it is a round trip, and the timing must account for return windows and for the alignment of Earth and the destination at both departure and return. This immediately connects the moving solar system map to the limits of human travel. A crew can survive only so long in transit and at the destination without resupply. If return windows are infrequent, a crew may have to wait months or years for a favourable return trajectory extending the mission duration. Mars missions illustrate this most strongly among near-term targets. A crew might travel for months, remain for a period, and then travel for months back with the stay duration constrained by the orbital cycle. The world does not wait. The window controls the schedule. This is a limit that comes from orbital motion, not from technology alone. The map of worlds also includes the Sun as a hazard and as a resource. Near the Sun, sunlight is strong and can power solar panels efficiently, but heat and radiation can be intense. Far from the Sun, sunlight is weak, making solar power less effective and increasing the need for alternative power sources. Farther out, communication becomes more delayed and weaker. These factors scale with distance in a predictable way, and they shape what kinds of missions are practical. The outer planets are not only farther in kilometers, they are farther in operational time and in energy requirement for arrival and departure. A human mission to Jupiter or Saturn would face not only multi-year travel times with known propulsion, but also increased radiation hazards in the region of Jupiter and significant system endurance requirements. The map therefore already hints at where human travel becomes difficult, even before the numbers are laid down. Another part of the moving map is the notion of reference frames. From Earth, planets appear to move against the stars. In mission design, the most useful frame is usually heliocentric, because the Sun dominates the dynamics. In this frame, the planets have nearly circular orbits, and spacecraft trajectories can be computed as orbits with small modifications. In the Earth-centered frame, the Moon dominates nearby space, but once a spacecraft departs Earth, the Sun-centered frame becomes the natural description. This matters because distance between worlds can be measured in several ways. It can be measured as instantaneous straight-line separation. It can be measured as the length of the transfer path. It can be measured as the energy difference between orbits. For human travel, energy difference often matters more than straight-line distance, because it determines how much propulsion and fuel are required. A world that is farther in kilometers might be easier to reach if the energy requirements align well, while a closer world might require a more difficult descent or ascent because of atmospheric conditions or gravity. In this section, the main result is that the solar system is a set of moving targets on predictable orbits. Distances between worlds vary over time. Travel is planned around windows when geometry supports efficient transfers. Routes are curved and timed because gravity makes free motion orbital. The definition of reaching a world depends on whether the mission is a flyby, an orbit, or a landing, and these definitions change the time and energy requirements. This moving map is the outer framework for understanding limits. The next step is to fix the ruler that measures the map in a stable way by establishing the astronomical unit and the translation of distance into light time, because the first universal limit on travel and contact is not propulsion. It is the speed at which information can move. A moving map needs a fixed ruler, and in the solar system that ruler is the Earth-Sun distance, because it anchors planetary spacing in a way that can be measured and reused. The average Earth-Sun distance is called the astronomical unit. Once it is known in kilometers, it becomes the unit that turns orbital sizes from ratios into concrete scales. It also provides a direct bridge from distance to time through light time, because the speed of light is constant and known. The outer region here is the establishment of this scale, and the way it becomes the first step toward understanding limits, because it immediately separates what can be moved physically from what can be communicated. The astronomical unit is not assumed, it is measured. Historically, it is inferred through geometric observations of planetary motion and rare alignments, and later it is refined with radar ranging. A radio signal is transmitted from Earth to a nearby planet such as Venus. The signal reflects and returns. The time delay is measured. Since the speed of light is known, the distance is calculated. This ties solar system distance to a physical constant, rather than to a chain of assumptions. The resulting value is about 150 million kilometers for one astronomical unit. With this number fixed, the solar system's scale becomes a set of multiples. Venus orbits at less than 1 astronomical unit. Mars orbits at more than 1. Jupiter orbits at about 5. Saturn orbits at about 9.5. These multipliers provide a simple sense of growth. Each step outward adds not a few percent, but factors. Yet kilometers remain difficult to hold in the mind beyond certain sizes. This is where light time becomes useful. Light travels at about 300,000 kilometers per second. If one divides 150 million kilometers by 300,000 kilometers per second, the result is about 500 seconds, which is a little more than 8 minutes. This means that the Sun is about 8 minutes away in light time. When Earth's orbit is used as the ruler, the solar system can be expressed in minutes and hours of light travel time. This immediately changes the meaning of distance. It shows that even in the near neighborhood, information is delayed. A message from Earth does not reach the Sun instantly. It reaches the Sun after minutes. A message from Earth reaches Mars after minutes that vary with alignment. A message reaches Jupiter after tens of minutes. A message reaches Saturn after more than an hour. This is the first clear limit. No matter how fast a spacecraft travels, information cannot travel faster than light within known physics. This limit applies equally to robots and to humans. It defines the maximum speed of contact. It also defines the minimum possible time to know what is happening in a distant place. The astronomical unit therefore does two things at once. It sets the physical scale of the solar system in kilometers, and it sets the communication scale in minutes. In human time, 8 minutes is a small but meaningful span. It is long enough to make real-time control impossible for events near the Sun. It is short enough that a delayed response is still within an ordinary work rhythm. As distances grow, the delay grows into tens of minutes, and then hours, and the rhythm changes. The distance between worlds in this view is first a distance between moments. If a probe at Mars sends a signal, Earth receives it many minutes later. If a probe at Saturn sends a signal, Earth receives it more than an hour later. This is not a limitation that can be overcome by better engines. It is a property of space-time as it is currently understood and measured. Light time also provides a way to express the distance between worlds without requiring imagination of enormous numbers. The Moon is about 1 1/3 seconds away in light time. This makes the Moon feel close in communication terms. Mars at close approach can be a few minutes away. At far alignment, it can be more than 20 minutes away. Jupiter ranges from around half an hour to nearly an hour. Saturn ranges from a little over an hour to roughly an hour and a half. These ranges come from orbital geometry and are not fixed. They change as planets move, but they remain within defined bands, and those bands can be used to describe what it means to operate in those regions. The light time also defines the earliest possible warning. If a crewed spacecraft near Mars experiences a problem and sends a distress signal, Earth cannot know until the signal arrives. The time to respond with advice or instructions is further delayed by the return light time. Even at Mars, this creates a control loop measured in tens of minutes to nearly an hour in the worst geometry. At the outer planets, the loop becomes hours. This makes local autonomy essential, whether the local agent is a spacecraft computer or a human crew. The astronomical unit also helps connect physical travel time to speed in a way that remains grounded. Travel time is always longer than light time because spacecraft speeds are far below light speed. A spacecraft moving at 10 kilometers per second covers about 860,000 kilometers in a day. In a year, it covers hundreds of millions of kilometers. These are large numbers, but when set beside the astronomical unit, they become manageable. One astronomical unit is 150 million kilometers. At 10 kilometers per second, it would take about 170 days to traverse one astronomical unit in a straight line at constant speed. In practice, interplanetary travel is not a straight line, and speed is not constant. But this simple conversion is enough to show why travel to even nearby planets tends to be measured in months. It also shows why travel to the outer planets tends to be measured in years. If a world is 5 astronomical units from the Sun, the scale of travel is multiple astronomical units from Earth, depending on alignment, and the travel time cannot be compressed into weeks without enormous energy. When distance is expressed in astronomical units and light time, the limits begin to look layered. Information is limited by light time, travel is limited by propulsion, and by the need to follow gravitational trajectories. The astronomical unit is the bridge between these limits because it is both a spatial unit and a unit of delay through a constant conversion. In a calm description, this is the first moment when the distance between worlds becomes inseparable from waiting. A decision made on Earth cannot have immediate effect on a distant spacecraft. It must be sent, it must travel, it must be received, confirmation must return. The loop lengthens with distance and no engineering can remove it. This does not make travel impossible, it changes how travel is managed. For robots, autonomy and pre-planned sequences are required. For humans, autonomy becomes a central requirement and changes risk management, because help cannot arrive quickly in either instruction or in physical rescue. Another aspect of the astronomical unit scale is how it relates to the Sun's influence. Solar energy decreases with the square of distance. At 2 astronomical units, sunlight is 1/4 of the intensity at Earth. At 5 astronomical units, it is 1/25. At 10 astronomical units, it is about 1/100th. This matters because it affects spacecraft power and thermal design. For human travel, it matters because the environment becomes colder, and because solar power becomes less effective, requiring larger arrays or alternative power sources. This scaling is not a new limit like light speed, but it is a practical limit on system design. It shows that distance between worlds is not only a distance to cross, it is a change in the available energy environment. Farther out, more of the mission must be carried from home in the form of fuel and power generation capability. The astronomical unit therefore becomes a quiet framework for understanding why human travel is more plausible in some regions than others. Near Earth, sunlight is strong, communication delay is small, and return is possible. Farther out, sunlight weakens, delays grow, and return times lengthen. In this section, the ruler is fixed. 1 astronomical unit is about 150 million kilometers and about 8 minutes of light time. With this, the solar system's distances become multiples, and distance becomes time both for signals and more slowly for travel. The next step is to take light time as the first hard limit and describe how it scales from seconds to hours and beyond, because this limit defines the boundary between immediate control and delayed autonomy which is one of the clearest operational limits on human travel between worlds. Light time is the cleanest limit in the distance between worlds because it converts space into waiting without any dependence on engineering choices. A spacecraft can be built larger or smaller. A rocket can be more powerful or less. A trajectory can be faster or slower. None of these change the time it takes for a signal to cross the distance at the speed of light. In human time, this limit shows up first as seconds, then as minutes, and then as hours, and each step changes how travel can be controlled and supported. The outer region here is this scaling of signal delay, and what it implies for the management of journeys, because even if travel could be made faster, the limit on information flow would still define a boundary between worlds. The scale begins near Earth. The Moon is about 1 1/3 seconds away in one-way light time. That means that a command sent from Earth arrives at the Moon a little more than a second later, and a reply arrives a little more than a second after that. The round-trip delay is only a few seconds. This allows near real-time guidance. It is not truly instantaneous, but it is close enough that a human controller can correct a lander's course or adjust a rover's actions with an almost immediate feedback loop. In practice, lunar missions still use automation because precision and safety are improved by onboard control, but the light time does not prevent direct supervision. The Moon therefore sits inside a region where human travel and human control remain closely linked. A crew on the Moon can speak to Earth with a noticeable but small delay. Ground teams can monitor and advise with only short pauses. This is the first step beyond Earth where distance exists but does not dominate time. The next scale is the inner planets. When Earth and Mars are relatively close, the one-way light time can be a few minutes. When they are far, the delay can be well over 10 minutes and can approach or exceed 20 minutes. Venus has similar minute scale delays. These numbers mean that the feedback loop for control becomes long. A rover on Mars cannot be driven like a remote car. If a command takes many minutes to arrive and the response takes many minutes to return, a single decision cycle becomes half an hour or more. By the time a human controller sees the result of a command, the rover has either executed it long ago or not at all. This forces a change in operating style. Rather than continuous control missions, since sequences are planned for the rover to drive a certain distance to stop to image hazards, to perform a measurement and to report. The rover executes the sequence autonomously, using onboard hazard avoidance and decision rules. Human teams plan a day of activity, send it, and then wait for results. This is not a matter of preference. It is the only practical way to operate under minute-scale delays. For human travel, the same limit applies. A crew at Mars cannot depend on Earth for immediate decisions. Medical advice, technical guidance, and problem-solving support can still be provided, but it arrives late. The crew must be trained and equipped to act without instant help. In emergencies, the delay can matter. If a life support anomaly develops, the crew must respond before Earth can even know. Earth can assist in analysis and in later steps, but the first response must be local. This is the first clear autonomy boundary for human missions beyond the Moon. The time delay begins to force self-reliance in minutes. The next scale is the outer planets. Jupiter is tens of minutes away in one-way light time depending on alignment. Saturn is more than an hour away. Uranus and Neptune are longer still. At these distances, the round-trip delay becomes multiple hours. This changes the nature of operations. A spacecraft near Saturn cannot be guided through an event in any interactive way. Orbit insertion burns close flybys, and instrument pointing sequences must be planned and uploaded well in advance, and the spacecraft must execute them on its own. Engineers cannot watch in real time and intervene if something goes wrong. They can only wait for the signal to return with the news. This is why deep space spacecraft are built with fault protection that can detect problems and place the spacecraft in a safe configuration automatically. The light time makes autonomy not a feature, but a requirement. For human crews, the same rule would be more severe. A crew near Jupiter or Saturn would face hours of delay to and from Earth. Immediate consultation would be impossible. Even routine collaboration would be stretched. Earth could send suggestions and receive updates, but the crew would be effectively independent in decision-making on the timescale of hours. In addition, physical rescue would be impossible within any useful time frame. This is not a claim about will. It is a result of distance and speed. Rescue would require travel times of years to the outer planets, even with robotic mission-level propulsion. Thus, the light time is paired with travel time to define a deep space boundary where human missions must be fully self-contained. The practical meaning of light time can also be seen in how it shapes scientific observation. Many measurements at distant worlds are time-critical. A spacecraft might pass behind a planet relative to Earth, creating a radio occultation that reveals atmospheric structure. A spacecraft might pass through a ring plane or a plume. These events happen on minute timescales and cannot be adjusted from Earth. The spacecraft's timeline must be correct. Its onboard clock must be accurate. Its pointing must be stable. In human time, this means preparation weeks in advance for events that last minutes, and then a long wait for confirmation that the event occurred as intended. This waiting is a defining rhythm of deep space work. Another aspect of light time is that it varies with orbital geometry. Planets move. Earth is not always at the same distance from Mars, Jupiter, or Saturn. The delay changes across months and years. For a mission, this means that the communication loop lengthens and shortens predictably. The delay is shortest near opposition, when Earth and the planet are on the same side of the Sun. It is longest near conjunction, when the planet is on the far side of the Sun. Conjunction also introduces another operational constraint: signals pass near the Sun and can be disrupted by the solar corona. During conjunction periods, missions may reduce communications or avoid critical operations because the link quality is lower. For human missions, this would be a planned period of reduced contact, reinforcing the need for autonomy. The light time limit therefore creates not only a constant delay, but a seasonal pattern of better and worse communication. The limit also scales beyond the solar system. When distance is measured in light years, the time for a signal to cross is measured in years. A signal to the nearest star takes more than 4 years to arrive. A reply takes more than 4 years to return. This defines a boundary where communication is no longer an operational tool for a mission in the usual sense. It becomes a historical record. For human travel, this makes Earth support essentially irrelevant in real time. Even robotic missions would operate as independent explorers. This is the far extension of the same rule already seen at Mars and Saturn. The scaling is smooth. Seconds at the Moon, minutes at Mars, hours at Saturn, years to the stars. At each step, the style of travel and control must change. The light time limit does not forbid travel. It forbids immediacy. It ensures that distance between worlds is also distance between moments. It also ensures that any technology designed for deep travel must include local decision-making capability, either in computers or in humans. This connects directly to the limits of human travel. A human crew can make decisions locally, which is an advantage compared with remote control. But humans also require supplies protection and health management, which become harder as the delay grows and as resupply becomes impossible. The autonomy requirement is therefore not sufficient by itself. It is a necessary condition that becomes increasingly demanding with distance. In the calm language of this script, light time is the first hard limit, because it is not a matter of engineering choice, and because it sets the pace of interaction with distant worlds. It turns the solar system into a hierarchy of operational zones. The Moon remains close in seconds. Mars becomes distant in minutes. The outer planets become distant in hours. Beyond that, stars become distant in years. The next step is to describe how physical travel differs from communication, focusing on how orbits replace straight lines and why the actual routes between worlds are curved and timed. This is the next layer of limits, because even if communication delay were acceptable, the energy and timing requirements of orbital travel set the months and years of flight that define how far humans can practically go. Once light time defines the limit on immediacy, the next limit is the shape of physical travel itself, because in space, the shortest line is rarely the path that is actually taken. Worlds are not fixed points on a flat map. They are bodies moving on orbits in a gravitational field dominated by the Sun. The outer region here is the replacement of straight-line travel with orbital transfer, because this change explains why distances between worlds translate into months and years, even when spacecraft move at speeds far beyond anything on Earth. A straight-line picture suggests that travel time is simply distance divided by speed. Space travel is not so simple, because a spacecraft cannot ignore gravity, and because it begins already in motion around the Sun. A spacecraft launched from Earth carries Earth's heliocentric velocity about 30 kilometers per second. It does not start from rest in the Sun's frame. To reach another world, it must change its orbit around the Sun so that its path intersects the destination's orbit at the time the destination is there. This means that interplanetary travel is at its core a problem of moving between orbits. The natural motion under gravity is an orbit, and thrust is used mainly to move from one orbit to another. A spacecraft therefore spends most of its journey coasting, not because it cannot thrust, but because coasting along a designed orbit is the most efficient use of limited fuel. The simplest efficient transfer between two circular orbits around the Sun is an ellipse that touches the departure orbit at one point and the destination orbit at another. The spacecraft is inserted into this ellipse by a brief engine burn near the departure point. It then follows the ellipse under the Sun's gravity until it reaches the destination distance. If it needs to match the destination's orbital motion, another burn is required. This basic pattern shows why straight lines are not the default. A straight line trajectory would require sustained thrust to keep the spacecraft from simply falling into a different solar orbit. Sustained thrust over months is possible in limited ways, but the energy and power requirements are large, and the resulting time is still constrained by the need to shape the path and meet a moving target. The orbital method uses gravity as an ally. It transforms a brief velocity change into a long controlled change in position. Time enters here through orbital periods. An orbit has a period determined by its size. Large orbits take longer. A transfer ellipse that reaches far from the Sun has a long period, so the time to travel along part of it is naturally long. This is why travel between worlds is often not a matter of pushing hard for a short time, but of selecting an orbit with the right size and timing. The route is a clock as much as a path. The destination does not wait, so timing is built in from the start. The world's motion sets launch windows because there are only certain times when an orbit that departs from Earth's position can intersect the destination's future position with a feasible energy. This creates waiting time before departure and sets the overall mission schedule. A clear example is travel to Mars. Mars is sometimes close and sometimes far, but the efficient transfer depends on where Mars will be months later. The transfer time is set by the chosen orbit. The result is that missions often take many months to reach Mars. Faster routes are possible with higher energy, but they require greater launch capability and often arrive with higher relative speed, which then must be reduced for orbit insertion or landing. The same logic scales outward. Travel to the outer planets can take years because the transfer orbits are larger and have longer periods. Even though spacecraft may move at tens of kilometers per second, the path length and the timing requirements produce long durations. This is not a sign of slowness, it is a sign of scale. In this orbital view, speed is not constant. A spacecraft moves faster when it is closer to the Sun and slower when it is farther away, even without thrust because of energy conservation in the gravitational field. If the spacecraft is sent outward, it climbs the Sun's gravitational well, converting kinetic energy into gravitational potential energy. Its heliocentric speed decreases as it moves outward. This means that the outward leg of a transfer naturally slows in the outer regions. The early part of the journey can cover distance more quickly. The later part covers distance more slowly. This is another reason simple division of a single distance by a single speed does not describe real flight time. The time is determined by the orbit's energy and geometry. Another reason straight lines fail is that distance between worlds changes during the flight. Earth moves. The destination moves. The distance between them grows or shrinks depending on the alignment. A spacecraft leaving Earth is not chasing a fixed point. It is intercepting. The correct aim is ahead of the destination along its orbit. This is like throwing an object to a moving target. The throw must lead the target. In interplanetary travel, the lead is large because the flight is long. An intercept can occur only if the spacecraft's orbit and the destination's orbit cross at the same time. This defines the intersection in both space and time. If the spacecraft arrives early, the destination is elsewhere. If the spacecraft arrives late, the destination has moved on. Thus, even if a straight path were possible, it would still require the correct timing and direction that account for motion. The orbital approach encodes this timing directly. The ellipse is chosen so that the travel time along it matches the destination's progress. This is why orbit mechanics and calendars are intertwined. Gravity also shapes how arrival is defined. A spacecraft can fly by a world without needing to match its speed closely. In that case, a high-energy trajectory can shorten travel time, but the spacecraft passes quickly, limiting the time available for close observation. To orbit the world, the spacecraft must reduce its relative speed enough to be captured, which requires fuel or other techniques. To land, it must reduce speed further and survive atmospheric entry or descent. These requirements can push mission designs toward longer transfers that arrive with lower relative speed, because a lower approach speed reduces the fuel needed for capture and can simplify entry profiles. For human missions, this is critical. A crewed mission cannot accept a fast flyby as a success in the same way. It must slow down, enter orbit or land, and it must preserve life support margins. That pushes designs toward trajectories that manage energy carefully, rather than simply minimizing time. Thus, the orbital nature of travel becomes a limit not only in flight duration but in energy management and safety at arrival. The curved path is also longer in distance traveled than the instantaneous straight-line separation between worlds. A transfer ellipse from Earth's orbit to Mars' orbit or to Jupiter's orbit is an arc around the Sun. The spacecraft may travel hundreds of millions or billions of kilometers along this arc, even if the direct separation at departure is less. The extra distance is not waste. It is the geometry of an orbit in a gravity field. For missions that use gravity assists, the path can be longer still. A gravity assist is a close pass by a planet that changes the spacecraft's heliocentric velocity by exchanging momentum with the moving planet. Gravity assists can reduce the propellant needed or allow a mission to reach a destination that would otherwise be too expensive in fuel. But they impose timing constraints and often add detours. The spacecraft must go where the assisting planet is not where it would like to go in a straight line. This can increase travel time even as it makes the mission feasible. Thus, in the real solar system, routes are often not direct transfers but sequences of arcs and encounters. Each encounter is a timed event. Between encounters are long coasts. Human time is therefore shaped by these phases. Months and years are divided by gravity assist dates, by correction burns, and by arrival opportunities. This is how distance becomes a schedule. The limit is not simply that worlds are far apart. The limit is that worlds are far apart in a system where free motion is orbital and where targets move. The route must respect these rules. That respect yields long durations for energy-efficient travel, and it makes the trade between time and fuel unavoidable. A faster route is possible by increasing energy, but it raises other burdens at departure and arrival. A slower route is possible by conserving energy, but it extends exposure to the deep space environment and extends mission duration. For humans, exposure and duration are not minor concerns. They are central constraints that grow with time. This is why the orbital nature of travel is a limit that becomes clearer as distance increases. The Moon remains close enough that travel can be measured in days and can be approached with comparatively direct paths. Interplanetary travel quickly becomes months and years because orbits and energy dominate. Beyond the planets, interstellar distances make the orbital method within the solar system irrelevant, and the problem becomes one of reaching velocities that are a substantial fraction of light speed, which introduces new limits. That step will come later. For now, the key result is that between worlds in the solar system, travel is a matter of changing solar orbits. Routes are curved and timed. The time required is tied to orbital period and energy, not to straight-line distance alone. With this understanding in place, the next step is to describe propulsion and energy costs more directly, because the limits of human travel depend on how much velocity change can be produced per unit mass, and how quickly energy demands rise as one tries to shorten travel time. If light time limits, immediacy and orbital motion, shapes routes, propulsion and energy, define the practical boundary of how quickly and how often worlds can be reached. The outer region here is the cost of changing velocity, because in space travel the main resource is not distance but delta V, the total change in velocity that a spacecraft or crewed vehicle can produce. Delta V is the currency that pays for leaving Earth changing solar orbit, capturing at a destination and returning. It is also the reason travel time cannot be reduced arbitrarily. To shorten time, a trajectory must be more energetic, which means higher speeds and larger velocity changes. Those velocity changes require energy and propellant mass grows rapidly as delta V requirements rise. This is why going faster becomes expensive, and why the limits of human travel are often limits of mass and energy, rather than limits of desire. Chemical propulsion provides high thrust, meaning it can produce large acceleration over short periods, which is essential for launch and for major maneuvers. Its limitation is that it consumes propellant quickly, and that the amount of propellant needed for a given delta V grows steeply. The reason lies in the rocket equation, which links the achievable delta V to the exhaust velocity of the propellant and to the ratio of initial mass to final mass. Without writing the equation, the consequence can be stated plainly. If a vehicle needs a modest delta V, it can carry a manageable amount of propellant. If it needs a larger delta V, it must carry much more propellant, and that propellant adds weight that itself must be accelerated, which requires even more propellant. This compounding effect is why rockets are mostly propellant at launch. It is also why deep space missions often use gravity assists and careful trajectory design to reduce propellant needs. For crewed travel, the compounding effect is more severe because a crewed vehicle must also carry life support systems, habitats, shielding and supplies which increase mass. More mass makes it harder to achieve high delta V, which then pushes travel time toward longer, lower energy routes. The delta V demands of leaving Earth are a first major step. Earth's gravity well is deep. To reach orbit requires several kilometers per second of velocity. To leave Earth and enter a heliocentric trajectory requires additional velocity. This means that every interplanetary mission begins with a large energy investment. For robotic probes, launch vehicles can provide most of this energy. For crewed missions, launch vehicles must lift much larger masses, which multiplies cost and complexity. Once in heliocentric space, changing the solar orbit to reach another planet requires additional delta V, which depends on the destination. Reaching Venus or Mars requires changing orbital energy by a moderate amount. Reaching the outer planets requires larger changes because the destination orbits are farther from the Sun. In energy terms, moving outward means raising the orbit's size. This is done by increasing heliocentric velocity near Earth's orbit, so that the new orbit's farthest point reaches the destination distance. The more the orbit must be raised, the more delta V is required at departure, unless gravity assists are used. Travel time is tied to this energy choice. A low-energy transfer uses less delta V, but takes longer because its orbit has a longer period. A high-energy transfer uses more delta V and takes less time because it is on a more energetic path. The practical limit appears when the required delta V becomes so large that propellant mass becomes unmanageable for the available launch capability. Another major delta V demand is arrival. To reach a planet in the sense of orbiting it, a spacecraft must reduce its speed relative to that planet enough to be captured. This is often called orbit insertion. For robotic missions, this can be done with a burn near the planet where the burn is most effective. For some planets, atmospheric drag can be used to slow down, but this adds thermal and control complexity and depends on having an atmosphere with suitable properties. For Mars, aerobraking has been used for some orbiters. For Venus, entry is possible but harsh. For the Moon, there is no atmosphere, so insertion requires propellant. For the outer planets, propellant requirements can be large, and missions often choose flybys instead of orbit insertion unless the mission is designed with sufficient fuel and a suitable approach. Cassini is a clear example of a mission that carries substantial propellant and uses gravity assist to arrive at Saturn with conditions that make orbit insertion feasible. For crewed missions, the arrival problem becomes larger. Entering orbit or landing requires precise control and large energy reduction. If a crew must also return, the mission must also include the delta V to depart the destination and return to Earth. This is the heart of the human travel limit. A robotic probe can travel one way and end its mission. A human mission must be designed for return or for long-term settlement, and long-term settlement would require local resources and infrastructure far beyond current capability. Thus, for near-term human travel, the delta V budget must cover a round trip, and this increases the mass and energy requirements sharply. The desire to shorten time adds another layer. Shorter travel time can reduce exposure to radiation and microgravity, which is valuable for human health, but shortening time generally requires higher energy, which means higher delta V and more propellant. This increases mass at launch and can increase risk. It also increases arrival speed, which can make orbit insertion and landing harder. Therefore, there is a trade between travel time and propellant mass that cannot be avoided with chemical propulsion. For a crewed Mars mission, for example, a faster transfer would reduce months in transit, but it would demand a larger departure energy and a more demanding arrival profile. The mass penalty might outweigh the health benefits unless new propulsion systems are used. This is why many mission concepts accept travel times of many months as a compromise. The propulsion limit is therefore not simply a limit on how far humans can go. It is a limit on how quickly they can go while carrying what they need to survive. Electric propulsion provides a different trade. Ion engines and other electric thrusters have high exhaust velocity, meaning they can produce large total delta V with relatively little propellant. Their limitation is thrust. They accelerate slowly. They must thrust for months or years to build up speed. This can be useful for robotic cargo and for some deep space missions, but for crewed travel, the long thrust period and the power requirements become challenging. High-power electric propulsion would require large solar arrays near the Sun or nuclear power. Far from the Sun, solar power weakens quickly. Nuclear power can provide steady power, but it adds complexity and mass. Electric propulsion can change what is feasible, but does not automatically make travel fast in human time unless power and thrust are high. In many cases, it supports efficient movement of cargo or gradual spiral transfers rather than quick crude journeys. Nuclear thermal propulsion, which heats propellant with a reactor and produces higher exhaust velocity than chemical propulsion, could reduce propellant mass for a given delta V, potentially enabling faster transfers for crewed missions. However, such systems have not been used operationally for human travel, and their development and safety concerns are substantial. The script does not assume their availability. It states the general principle: higher exhaust velocity reduces the propellant mass needed for a given delta V, which can ease the time versus mass trade. Yet the limits still remain: energy must come from somewhere, and mass must still be accelerated. Another propulsion-related limit is shielding. As speed increases, impacts with dust and small particles become more energetic. As travel time increases, exposure to radiation accumulates. Shielding can mitigate both, but shielding adds mass. Added mass increases propellant requirements. This creates a feedback loop in mission design. The vehicle needs shielding to protect humans, but shielding increases mass, which increases delta V requirements, which increases propellant mass, which increases launch mass. This loop is one of the central reasons human travel beyond nearby worlds is hard. It is not a single obstacle. It is a coupled system of constraints where solving one problem worsens another. In the calm view, propulsion and energy costs define a practical envelope. Within the inner solar system, robotic missions can reach many worlds by choosing efficient transfers and using gravity assists. Crewed travel can reach the Moon, and with major effort could reach Mars within months, but it faces a tight balance of mass life support and exposure. Beyond that, the travel times become years, and the mass and shielding requirements rise, while resupply becomes impossible, making the envelope narrower. This section therefore frames the limits as a resource accounting. Delta V is costly. Propellant mass grows rapidly with required delta V. Faster transfers demand higher energy and often higher arrival speed, creating additional burdens. Crewed missions must carry mass for survival and protection, tightening the trade. With this propulsion limit clarified, the next step is to describe how gravity assists can partially substitute for propellant, allowing missions to reach farther worlds with smaller launch energy, while also imposing timing constraints that can lengthen travel time. This will add another layer to the distance between worlds as a problem of calendars as well as of engines. Gravity assists are one of the main reasons robotic spacecraft can reach distant worlds with limited propellant, because they allow a spacecraft to change its heliocentric velocity by borrowing momentum from a moving planet. The outer region here is this gravitational exchange as a tool for extending reach, because it shows how distance between worlds is not only a matter of engines, but also a matter of timing. A gravity assist is not magic, and it does not create energy from nothing. The planet is already moving around the sun. The spacecraft approaches the planet, is bent by the planet's gravity, and departs on a new direction. In the planet's frame, far from the planet, the spacecraft's speed before and after the encounter is nearly the same. What changes is the direction. When this motion is translated back into the sun's frame, the change in direction can produce a change in the spacecraft's heliocentric speed and energy. The spacecraft can gain energy from the planet's orbital motion, or lose energy to it depending on the geometry. The planet's own motion changes by an immeasurably small amount because the planet is so massive compared with the spacecraft. This is the physical basis of the assist. The benefit is that the spacecraft can change its trajectory without burning large amounts of propellant. The cost is that the spacecraft must meet the planet at a very specific time and place to achieve the desired outcome. This turns gravity assists into a scheduling tool as much as an energy tool. A spacecraft cannot ask for a gravity assist whenever it wants. It must arrive when the planet is there. It must pass at the correct distance and angle. It must also pass within safe limits, avoiding atmospheres, rings, or radiation belts depending on the planet. These requirements impose a narrow corridor in space and time. A gravity assist therefore creates constraints that can lengthen the journey, even as it saves fuel. The spacecraft may have to travel inward toward the Sun and then outward again. It may have to loop past Earth one or more times. It may have to wait in solar orbit for the alignment to be right. Each of these adds time. In human terms, a gravity assist can turn a direct route of several years into a longer route of several more years. Yet it can also make the mission possible at all if the launch vehicle cannot provide the required departure energy for a direct transfer. This is why gravity assists are central to the history of deep space exploration. They allow small engines and limited propellant to accomplish large changes in solar orbit. They also reveal the distance between worlds as a network of moving opportunities rather than as a simple set of gaps. The classic gravity assist targets are Venus, Earth, and Jupiter because of their mass and orbital speed. Venus is closer to the Sun and moves faster around it. A spacecraft can fall inward toward Venus, gain speed by descending in the Sun's gravity well, and then use a Venus flyby to change direction and energy. Earth itself can be used for an assist by looping back after an inner planet encounter. Jupiter is massive and can produce large deflections and large changes in heliocentric trajectory. A Jupiter flyby can boost a spacecraft outward to Saturn and beyond, or it can redirect a spacecraft to different inclinations and different parts of the solar system. These are not abstract possibilities. They are techniques used in missions such as Voyager, Galileo, Cassini, and many others. The key point for limits is that gravity assists help robotic missions overcome the propellant mass problem described earlier. They reduce the delta V that must be produced by onboard engines. In some cases, they reduce the launch energy requirement by allowing the spacecraft to be launched on a less energetic trajectory, and then build energy gradually through encounters. For a mission to the outer planets, this can be the difference between feasibility and infeasibility. However, for human travel, gravity assists have a different meaning. A crewed mission cannot easily accept long looping trajectories that add years because human life support and radiation exposure impose time-linked constraints. A gravity assist route that saves propellant but adds years might be acceptable for a robot, but unacceptable for a crew. This is a central contrast. Gravity assists can extend reach, but they often do so by trading time for fuel. For humans, time is not a cheap resource. Time in deep space is exposure. It is consumables. It is risk. This is why gravity assists, while powerful, do not automatically expand human travel limits in the same way they expand robotic reach. They can still be useful, especially for moving cargo or for shaping trajectories in ways that reduce propellant mass, but the time cost must be weighed against human constraints. Another dimension of gravity assists is that they can also be used to reduce energy, not just to increase it. A spacecraft can use an assist to slow down relative to the Sun, helping it to enter orbit around a destination or to fall inward. In the outer solar system, a spacecraft approaching a planet at high speed can sometimes use moon flybys to reshape its orbit and reduce energy in steps, a kind of gravitational braking. In the Saturn system, for example, repeated flybys of Titan can be used to change a spacecraft's orbit around Saturn without expending large amounts of propellant. This is not a substitute for initial capture, but it can reduce the propellant needed to reshape the orbit after capture. For a crewed mission, such techniques could in principle reduce propellant requirements for operations within a planetary system, but they would also add time. A tour that takes years may be fine for a long robotic mission, but less suitable for a crew. Thus, again, the core pattern repeats: gravity can substitute for fuel, but often at the cost of time. Gravity assists also impose windows. If a mission requires a Venus flyby, followed by an Earth flyby, followed by a Jupiter flyby, the launch date must be chosen so that each encounter happens at the correct moment. The planets involved must align in a way that supports the sequence. This can restrict launch opportunities more than a direct transfer would. The window might open only in certain years rather than annually. This is part of what makes some mission plans rare. It also makes the preparation timeline more rigid. For human missions, a narrow window adds risk, because delays in development could postpone the mission by years. For robotic missions, postponement is costly but more manageable. This difference again highlights how human limits include institutional and logistical limits, not only physical ones. The deeper meaning of gravity assists for the distance between worlds is that the solar system is not a set of static distances, but a dynamic system with pathways that open and close over time. The planets act like moving waypoints. A spacecraft can use them as stepping stones in energy space, not in distance space. The stepping stones are not points to stop at. They are regions of influence that reshape motion. This makes the solar system more navigable for robots because a robot can spend years following a path that includes multiple encounters. It makes the solar system less straightforward for humans because each added encounter adds time and exposure. Still, even for humans, the concept matters because it shows that the limits of travel are not only determined by direct propulsion, they can be influenced by trajectory design and by the use of natural gravitational fields. Another practical aspect is risk. A gravity assist requires a close pass by a planet, sometimes within thousands of kilometers or less, depending on the mission. Navigation must be precise. Small errors can lead to a miss or to a dangerous approach. For robots, this risk is accepted with careful planning and redundancy. For humans, the risk tolerance may be lower because the consequences are higher. Passing close to Venus or Jupiter also exposes a spacecraft to different radiation environments and thermal conditions which must be managed. These are additional constraints that can offset the fuel savings. The calm conclusion is that gravity assists expand what robots can do by turning planetary motion into usable energy changes. They reduce propellant needs and enable distant missions. They do so by imposing timing and path constraints that often increase travel time. For humans, this time cost is more serious because it increases exposure and life support demands. Gravity assists therefore illustrate a broader rule about the limits of human travel techniques that make distance easier for machines, do not always make it easier for people because people carry time-dependent vulnerabilities. With this layer added, the next step is to move inward from physics and trajectories to the biological and life support limits that activate during months and years in deep space. That is where the distance between worlds becomes not only a question of reaching a destination, but of maintaining human bodies and human systems long enough to complete the trip. When trajectories and energy budgets are translated into months and years, the limits of human travel become biological and environmental as much as mechanical. Space between worlds is not simply empty. It is an environment shaped by radiation, microgravity, isolation, and the need for closed life support. The outer region here is the human body and its supporting systems in deep space, because these constraints grow with time and can become the dominant limit long before the physical ability to move between worlds runs out. The first major factor is radiation. On Earth, the atmosphere and the planet's magnetic field provide substantial protection from energetic charged particles. In orbit close to Earth, some protection remains because the magnetic field still deflects many particles, though astronauts still experience higher radiation than on the ground. Beyond Earth's immediate magnetic protection, in interplanetary space, radiation exposure increases. The radiation environment includes two main sources. One is solar energetic particles, bursts of high-energy protons, and other particles released during solar flares and coronal mass ejections. These events can produce short-term spikes in radiation dose. The other is galactic cosmic rays, high-energy particles from outside the solar system that are present continuously. Cosmic rays are harder to shield because of their high energy, and they can produce secondary radiation when they strike shielding materials. The cumulative exposure during months and years in interplanetary space is therefore a central concern. It is not only a long-term health risk, it is also an operational constraint because a large solar particle event could deliver dangerous doses without adequate shielding. A crewed vehicle must include a storm shelter, a region with extra shielding where the crew can take refuge during solar events. This shelter adds mass. Added mass increases propulsion demands. This is a direct link between biology and the propulsion limits described earlier. Radiation therefore acts as a limit both by its effects on health and by the mass penalty required for mitigation. The second major factor is microgravity. In the absence of gravity, human physiology changes. Muscles atrophy because they are not supporting body weight. Bones lose mineral density because they are not under normal loading. The cardiovascular system adapts to a different fluid distribution, and this can create difficulties when returning to a gravity environment. These changes begin quickly and accumulate over time. Exercise and nutrition can mitigate them, but they do not eliminate them completely. Long-duration stays on space stations show that humans can live in microgravity for months, and even more than a year, but the effects are significant and require extensive countermeasures. For travel between worlds that takes many months, microgravity is therefore a serious constraint. It is a time-linked constraint. The longer the mission, the greater the cumulative change and the harder the recovery. One mitigation is artificial gravity through rotation, such as a spinning habitat that creates a centrifugal acceleration. This could reduce physiological decline, but it introduces engineering complexity, mass, and structural requirements. It also affects how propulsion and docking are handled. Again, mitigation adds cost and complexity, which feeds back into the mass and energy limits. The third factor is life support. A crew cannot carry unlimited consumables. For missions beyond the moon, resupply is not practical. Life support must be reliable and must be capable of recycling air and water to reduce mass. Oxygen can be generated from water through electrolysis, but this requires power and systems. Carbon dioxide must be removed from the air and either stored or processed. Water must be recycled from humidity and waste. Food is harder to recycle fully, so most concepts still rely on stored food for the mission duration. The longer the journey, the more food must be carried, increasing mass. Closed-loop systems can reduce some needs, but they introduce complexity and failure modes. Reliability becomes a limit. A life support system must operate continuously for months or years. Redundancy can improve reliability, but redundancy adds mass. Spare parts can reduce risk, but spares add mass. Maintenance must be possible in flight. The crew must be trained and equipped to repair systems without outside help. Communication delays to Mars can be tens of minutes. To the outer planets, they are hours. Even at Mars, immediate guidance is impossible. This means life support must be designed for local troubleshooting. This is another way the light time limit turns into a human limit. The fourth factor is medical care. In deep space, a crew cannot quickly return to Earth. A medical emergency must be managed with limited resources. The vehicle must carry medical equipment and medications, and crew members must have training. Some conditions can be treated. Others might be fatal without advanced care. The risk increases with mission duration because the chance of an unexpected event rises with time. This does not imply that long missions are impossible, but it implies that risk accumulates. Mitigation again adds mass and complexity. The fifth factor is the psychological and social environment. A crew confined for months or years in a small habitat faces stresses, isolation, monotony, disrupted sleep cycles, and interpersonal strain. These are not abstract. They affect performance and health. Careful crew selection, training schedules, and communication can mitigate but not eliminate these stresses. Communication delays also change the feeling of connection to Earth. At the Moon, conversation is nearly immediate. At Mars, replies come after many minutes. This changes social support. At the outer planets, the delay would make real conversation impossible on the timescale of daily emotions. The crew would be functionally isolated from Earth's immediate feedback. This is a distinct psychological limit that grows with distance. It reinforces the requirement for autonomy and for onboard support structures. The sixth factor is the environment of the vehicle itself. Deep space is cold and in vacuum. Thermal control must keep systems within safe temperatures. Electronics must survive radiation. Micrometeoroids and orbital debris are hazards. In interplanetary space, debris is less dense than in Earth orbit, but micrometeoroid impacts still occur. Over long durations, small impacts can degrade surfaces and can pose risks. Shielding can mitigate impacts, but again adds mass. The vehicle must also manage propellant for attitude control and course corrections. Small leaks and small inefficiencies can matter over years. The seventh factor is the destination environment. If the destination is Mars entry, descent and landing present challenges, because Mars has an atmosphere thick enough to produce heating, but thin enough that parachutes alone are not sufficient for heavy vehicles. Large payload landings require complex systems. For the moon, landing requires propulsive descent. For asteroids, microgravity operations require careful anchoring. For the outer planets, there is no solid surface to land on. Moons might be targets, but they often sit within harsh radiation environments and far from Earth. Thus, the destination can add constraints that influence travel time and mission design. A mission might accept a longer, slower approach if it simplifies arrival or improves safety margins. For humans, safety margins matter. This can push designs toward longer, lower energy transfers rather than shorter, high energy ones. In this way, biological constraints and mission design constraints reinforce each other. The time spent in transit is exposure time. Shortening it is desirable, but shortening it requires more energy and mass which can be constrained. Extending it saves energy but increases exposure. This is the central tension in human interplanetary travel. It is a tension that does not appear as strongly for robots, which do not need air, water, and protection from microgravity. Robots have different vulnerabilities such as component aging and radiation effects on electronics, but their survival envelope is different. Human travel is limited by the need to keep a complex biological system stable in a hostile environment for long periods without resupply. These are not philosophical limits. They are engineering and medical limits expressed in time. A mission of days like a lunar trip can carry open-loop consumables and accept a higher risk profile. A mission of months like a Mars trip requires advanced life support and careful radiation management. A mission of years like a journey to the outer planets multiplies the challenges and pushes beyond what has been demonstrated for human spaceflight. This section therefore defines why human travel limits emerged long before the ability to send robotic probes runs out. Humans require more mass, more protection, and more reliability, and those requirements grow with duration. The next step is to translate these constraints into timescales for crewed missions in the near and mid-range, comparing what months and years mean for mission architecture, and why the envelope of feasible human travel remains concentrated close to Earth, even as robotic exploration extends much farther. The limits described so far become clearer when they are placed onto the actual timescales that crewed missions would face, because months and years are not only durations, they are exposure periods, supply periods, and reliability requirements. The outer region here is the calendar architecture of crewed missions, because this shows how distance between worlds translates into specific mission lengths, and why, with known propulsion and current support systems, human travel remains concentrated in the near region of the solar system. The Moon sits at the shortest crewed travel times beyond Earth. A lunar mission can be measured in days from departure to arrival, and in days or weeks for total mission duration depending on surface stay. Communication delay is seconds. Return is possible within days. This means that consumables can be carried without extreme mass, and the crew can rely on Earth support in a near-real sense. Medical emergencies can be addressed by returning relatively quickly. The lunar environment is harsh, but the timescale limits how long hazards must be endured. This is why the Moon remains within a practical envelope for human travel, even with limited propulsion. The next step outward is not a single world, but a set of destinations in cislunar space and near-Earth space, such as orbital platforms, asteroid flybys, or deep space excursions that still remain within weeks or a few months of return. These missions extend exposure, but keep return times shorter than interplanetary travel. They act as intermediate steps because they allow life support and shielding systems to be tested over longer durations while still allowing rescue or return. In human time, they sit between days and months. They reveal the transition where time begins to dominate risk. Beyond that, Mars defines the first full interplanetary human mission challenge. With efficient transfers using known propulsion travel times are on the order of many months each way. This already exceeds the duration of a typical Earth orbit mission by a large factor, and requires a vehicle that can support a crew for more than a year, when outbound travel, surface stay and return travel are combined. The surface stay is not optional if the mission is a round trip constrained by orbital windows. Because Earth and Mars align favourably only on a repeating cadence, a crew that arrives at Mars may need to remain until the return window opens. This can extend the mission significantly. Thus, a crewed Mars mission is not simply travel time to Mars plus travel time back. It is travel time plus waiting time imposed by celestial mechanics plus travel time. This makes the total mission duration a function of orbital geometry. A shorter outbound trip does not necessarily shorten the total mission if it causes arrival at a time that leads to a long wait for return. Mission designs attempt to balance these factors by choosing departure and return trajectories that yield a workable total time. In human terms, this means the crew must be prepared for a long period away from Earth, on the order of 1 to several years depending on the chosen architecture. Life support must be reliable across that span. Radiation exposure must be managed across that span. Microgravity exposure must be managed across the transit portions of that span. The crew must also operate on Mars, which adds further needs such as habitat protection, power generation, dust management, and medical support. This is why Mars is a threshold. It is not only farther than the Moon, it forces mission duration into a regime where time-driven constraints become dominant. These constraints include the cumulative radiation dose over many months, the physiological changes of microgravity, the mass of food and spares, and the psychological demands of long isolation with communication delay. The limits on human travel are therefore not only about reaching Mars, they're about sustaining a safe mission duration under these constraints. Even if a vehicle could be made faster, the mass and energy cost of doing so may be too high for practical launch, and may create other risks at arrival. Thus Mars sits near the edge of what is considered plausible, with major engineering effort while still remaining inside a timeline that is not measured in decades. Beyond Mars, the inner solar system also includes Venus and Mercury, but these worlds are not natural targets for crewed surface missions due to their environments. Venus has extreme surface conditions, and Mercury has harsh temperature swings and is deep in the Sun's radiation environment. Human missions might in principle pass near these worlds, but the relevance to limits is that not every closer destination is more accessible for humans. Environmental conditions can make a world effectively unreachable in practical terms even if it is nearer in kilometers. This reinforces that distance between worlds is a compound concept. It includes physical distance, travel time, and environmental suitability. The outer planets shift the timescale again. Reaching Jupiter or Saturn with known propulsion is measured in years for robotic missions. For humans, years in transit create a steep increase in exposure and logistics. Even if propulsion could carry a crew to Jupiter in a few years, the crew would face prolonged radiation exposure in interplanetary space, and then intense radiation near Jupiter. Saturn's radiation environment is less severe than Jupiter's, but the travel time is longer. In both cases, the communication delay is tens of minutes to hours, removing immediate Earth support. Rescue is not realistic. Return would add further years. A round trip to an outer planet would likely demand a total mission duration measured in many years, potentially approaching a decade depending on trajectories and mission profile. This pushes beyond what has been demonstrated for human spaceflight, and beyond what current life support and shielding systems are designed to handle. This does not imply it is impossible in all time. It implies that with current and near-term technology, the timescale pushes into a regime where the mass of supplies, the reliability requirement, and the health risk become dominant constraints. The envelope of feasible human travel therefore narrows sharply beyond Mars. A different class of destination is the near-Earth asteroids. Some asteroids have orbits that bring them near Earth and can be reached with relatively modest delta-v compared with Mars, though the travel time can still be weeks to months depending on the target. These missions could be significant for human exploration because they can extend deep space exposure without requiring planetary landing. They still involve microgravity operations and isolation, but they can be planned to keep total mission duration shorter than a Mars surface mission. This shows that human travel limits are not strictly radial. They depend on orbital accessibility. Some small bodies may be reachable within a timescale that is manageable even if they are not a planet. Yet these missions also illustrate the difficulties of operating in microgravity around an irregular body and of managing life support without easy return. In terms of timescale, they sit between lunar missions and Mars missions. They can be used to test the limits of endurance and autonomy. The core message of this section is that human travel timescales cluster because constraints cluster. Day-scale missions are feasible because consumables and exposure are limited and return is quick. Month-scale missions begin to stress life support and health, but may be manageable with robust systems. Multi-year missions push into a regime where cumulative risks and mass requirements become severe. This is why human exploration remains near Earth, even as robotic missions travel for years to the outer planets and beyond. Robots can be designed for long durations and can accept one-way missions. Humans cannot accept long durations without addressing radiation microgravity and life support at a much higher level. The distance between worlds therefore becomes a practical boundary, not at a particular kilometre mark, but at a particular mission duration mark. The threshold between months and years is especially important. It is the point where closed-loop life support and serious radiation protection become unavoidable. It is also the point where psychological and operational autonomy become central. Within the solar system, this threshold lies between Mars-class missions and outer planet-class missions. This section remains within the solar system timescale. It sets the stage for the next outward step, the boundary of the solar system itself. That boundary introduces distances that push travel into decades even for robotic craft, and would push human travel into durations that are not compatible with current life support and health constraints. By describing the heliosphere and the Kuiper belt as regions reached over decades, the next section will show how quickly the calendar expands outward, and how the limits of human travel emerge not only from physics, but from the simple arithmetic of time. Beyond the orbits of the giant planets, the solar system does not end suddenly. It thins into wider regions where the sun's gravity still dominates, where small icy bodies are common, and where the solar wind continues to push outward until it meets the interstellar medium. The outer region here is the boundary zone of the solar system because it shows how travel time expands from years into decades even for robotic spacecraft, and why the limits of human travel become sharply defined by simple duration before questions of destination even arise. Past Saturn and Uranus lies the region commonly associated with the Kuiper Belt, a broad population of icy objects beyond Neptune's orbit. Even farther at thousands of astronomical units lies the more distant reservoir often called the Oort cloud. These regions are not sharp walls. They are distributions of objects and influences that fade gradually with distance. For travel, what matters is that the distances involved are multiple tens of astronomical units, and then hundreds and thousands. In human time, these distances translate into decades at the speeds achieved by the fastest deep space probes. A spacecraft leaving the inner solar system does not travel at a fixed speed, but some missions achieve a relatively high asymptotic speed with respect to the Sun after their planetary flybys are complete. This speed is still tiny compared with the speed of light, but it is high enough that over decades it carries the spacecraft across the outer regions. The most instructive examples are the long-lived probes that have travelled beyond the major planets and into the outskirts of the Sun's influence. Their journeys are measured not in years to a single encounter, but in decades of steady outward motion, with milestones that are defined by crossing invisible boundaries rather than arriving at a planet. The most discussed boundary is the heliosphere, the bubble carved out in interstellar space by the solar wind. The solar wind is a stream of charged particles flowing outward from the Sun. Near Earth it is still moving fast, but it becomes more tenuous with distance as it spreads out. Far from the Sun, the outward pressure of the solar wind is balanced by the pressure of the interstellar medium, the thin gas and plasma between stars. Where the solar wind slows abruptly is called the termination shock. Beyond that is the heliosheath, where solar wind material is compressed and disturbed. Farther still is the heliopause, where the influence of the solar wind gives way, and the interstellar medium dominates. These boundaries are not rigid shells. They shift with solar activity and with variations in the local interstellar environment. Still, they provide a useful map of the solar system's outer reach in physical terms. Crossing them takes decades. This is a distance that is hard to express in kilometers without losing intuition, but it can be expressed in astronomical units. The heliopause lies on the order of 100 astronomical units from the Sun, though its exact distance differs by direction and changes over time. 100 astronomical units is about 100 times the Earth-Sun distance. Since 1 astronomical unit is about 150 million kilometers, 100 astronomical units is about 15 billion kilometers. A spacecraft moving outward at a speed of about 10 to 20 kilometers per second would take many years to cover this distance, and real missions show that the times are indeed measured in multiple decades from launch to heliopause crossing. In human time, that span is long enough that an entire generation can pass. Spacecraft systems must survive extreme longevity, and the teams that built them may retire before the mission reaches its far milestones. Yet robotic travel can still function because spacecraft can be designed to operate autonomously, and because power systems such as radioisotope generators can provide electricity for decades at reduced levels. This is an example of a regime where robots remain practical and humans do not, because human life support over decades in deep space is beyond demonstrated capability and would demand vast mass and reliability. The communication delay at these distances also becomes large even within the solar system. At 1 astronomical unit, light time is about 8 minutes. At 100 astronomical units, one-way light time is about 800 minutes, which is more than 13 hours. Round-trip delay becomes more than a day. This changes the nature of any control and support. A spacecraft beyond the heliopause must operate with extreme autonomy, not because it is intelligent in a human sense, but because waiting for guidance is too slow for many events. For human travellers, such delays would make Earth support nearly irrelevant for immediate decision-making. The crew would be functionally isolated from Earth's real-time problem-solving. In addition, rescue or return would be unrealistic. Even if a crew could travel that far, returning would take comparable time, turning a mission into a decades-long commitment. Human time in this region becomes lifetime time. The Kuiper Belt, which lies roughly from just beyond Neptune to several tens of astronomical units, offers another way to see the expansion of time. Neptune orbits at about 30 astronomical units. Objects in the Kuiper Belt lie beyond that. A mission from Earth to a Kuiper Belt object can take many years, even with gravity assists and high launch energy. The travel time is not defined only by distance, but by the need to intercept a small target on a specific orbit. The New Horizons mission, for example, uses a fast trajectory and a Jupiter flyby to reach Pluto, which is a Kuiper Belt object, in the broad sense of being part of that outer population. It takes about 9.5 years from launch to Pluto flyby. This is a clear human time marker, nearly a decade to reach a single world, even with a fast path designed for a flyby. The mission continues onward to another Kuiper Belt object and requires additional years. This illustrates the basic scaling. When distances reach tens of astronomical units, the travel time to a destination becomes a large fraction of a human decade. For robots, this is achievable with careful planning and long-lived systems. For humans, it becomes a major barrier because the mission duration would expose a crew to deep space radiation for years, require life support without resupply for years, and require psychological endurance for years, with increasing communication delays. The environment also changes. Farther from the sun, sunlight becomes weak, making solar power less effective and pushing missions toward nuclear power sources. Thermal conditions become colder and more uniform. The cosmic ray environment remains, and the lack of Earth's magnetic shielding remains. For robots, the primary challenges are power and system longevity. For humans, the challenges are life support and health over years. The boundary of the solar system therefore acts as a boundary of practical human travel under current assumptions, not because the distance is in principle insurmountable, but because the time required pushes into a regime where known human support systems become too heavy and too risky. Another feature of the outer solar system is that the notion of destination becomes less singular. A spacecraft can pass through regions where objects are small and widely spaced. Reaching a specific object requires precise navigation, but much of the journey is through empty space where the mission's milestones are defined by distance markers, such as crossing a planet's orbit, crossing the termination shock, or crossing the heliopause. These are boundaries in the distribution of particles and fields rather than visible landmarks. In human time, this makes the journey feel like long intervals punctuated by rare events. This is true even for robotic missions. For human travelers, a journey dominated by long intervals would require a stable, sustainable life for years, with few external changes which add psychological and logistical burdens. The limit is not only that the journey is long, it is that the journey is long in a monotonous environment with delayed communication and no rescue. When the solar system's boundary is described this way, the next step outward becomes unavoidable. If reaching the heliopause takes decades at current deep space speeds, reaching even the nearest stars takes far longer unless speeds increase by orders of magnitude. The light year becomes the next scale unit, and human time shifts from decades to centuries and beyond. This is the point where distance between worlds becomes distance between stellar systems, and the limits of human travel become dominated by the difficulty of attaining and sustaining a significant fraction of the speed of light while keeping people alive and protected. The solar system boundary therefore serves as a calm pivot. Within the solar system, travel times to planets are years, to the Kuiper Belt are years to a decade, and to the heliopause are decades. These are already long in human time, yet they're still within the operational reach of robotic spacecraft. For humans, the practical envelope tightens as the calendar stretches. The next section will introduce the nearest stars and the light year, and it will show with the same steady translation into human time why interstellar distances turn even the fastest solar system travel into a slow approach measured in centuries at current propulsion speeds. When travel moves from the outer edge of the solar system to the nearest stars, the scale changes so sharply that the familiar units of astronomical units and decades begin to feel insufficient. The outer region here is the light year and the nearest stellar neighbourhood, because this is where distance between worlds becomes distance between star systems, and where the limits of human travel are set by the large gap between the fastest speeds achieved by spacecraft and the speed that would be needed to make the trip fit within a human lifetime. A light year is not a unit of time, it is a unit of distance defined by a time. It is the distance light travels in 1 year. Because light travels about 300,000 kilometers per second, it covers an enormous distance in a year, about 9.5 trillion kilometers. This number is difficult to picture, but it can be used as a stable conversion. The nearest star system to the Sun, Proxima Centauri, is a little more than 4 light-years away. That means that even a radio signal travelling at the speed of light takes more than 4 years to reach it, and more than 4 years to return. Communication with a probe near that star would have a round-trip delay of nearly a decade. This immediately shows that interstellar travel is not simply an extension of deep space missions. It is a shift into a regime where Earth cannot meaningfully supervise in the way it does even for distant spacecraft. Even more important for human travel is physical speed. The fastest spacecraft leaving the solar system have speeds on the order of tens of kilometers per second relative to the Sun. This is fast by any Earth standard, but it is extremely slow compared with the speed of light. 10 kilometers per second is 36,000 kilometers per hour. Light moves at 300,000 kilometers per second, which is 30,000 times faster. Even 20 kilometers per second is still 15,000 times slower than light. When this speed gap is applied to a distance measured in light years, the time grows very large. A spacecraft travelling at 20 kilometers per second would take about 15,000 years to travel 1 light year. For a distance of 4 light years, the travel time becomes tens of thousands of years. This is far beyond any human lifetime, and far beyond the endurance of any engineered system known today. This is the core limit of interstellar human travel under current propulsion. The speed is too low by orders of magnitude. To make the trip to the nearest stars fit within human time, as lived within 1 lifetime, the vehicle must travel at a substantial fraction of the speed of light. Even 1/10 of the speed of light would make a 4 light-year trip take about 40 years in the simplest straight-line view. That is still a large fraction of a human lifetime, and would be longer when acceleration and deceleration are included. At 1/5 of the speed of light, the trip would take about 20 years, plus additional time for acceleration and braking. These are the kinds of speeds required for interstellar travel to become a human lifetime project. They are far beyond what chemical rockets can provide. They are beyond what current electric propulsion can provide for large vehicles. They demand entirely different energy scales. This is where the limit becomes an energy limit in an absolute sense. The kinetic energy of a vehicle increases with the square of its speed. To increase speed from 20 kilometers per second to 30,000 kilometers per second, which is 1/10 of light speed, the speed increases by a factor of 1,500. The kinetic energy per unit mass increases by the square of that factor, which is more than 2 million. This means that per kilogram of vehicle mass, the energy required to reach that speed is millions of times larger than the energy per kilogram associated with current deep space spacecraft speeds. This is not a minor engineering challenge, it is a regime change in energy management. Any realistic discussion of human interstellar travel must therefore address how such energy could be produced, stored, directed, and used safely. The script does not claim such systems exist. It describes the limit without a breakthrough in propulsion. Energy density and efficiency interstellar travel cannot fit within human time. Even if a vehicle could reach high speed, other limits appear. at a substantial fraction of light speed, impacts with dust and gas become extremely energetic. In the solar system, dust impacts are manageable at tens of kilometers per second with shielding. At 1/10 of light speed, even tiny grains would carry enormous kinetic energy relative to the vehicle. Shielding would need to be far more robust, adding mass, which increases energy requirements further. Interstellar space is thin, but it is not empty. There is gas and there are dust grains. Over a journey of light years, the vehicle would encounter many particles. Each would be a high-energy collision. This becomes a limiting factor for both robotic and human vehicles. For a robotic, probe damage might be acceptable if redundancy exists and if the mission is one way. For a human vehicle, shielding must protect life and critical systems. That adds mass and complexity. Another limit is radiation. Beyond the heliosphere, the sun's protective influence is reduced, and the cosmic ray environment is more directly experienced. Over decades, radiation exposure would be substantial. At high speeds, additional radiation effects appear because of interactions between the vehicle and the interstellar medium. Managing radiation would require heavy shielding or active protection, again adding mass and energy demands. Life support becomes a deep challenge over decades. A crewed interstellar mission, even at high speed, would likely take decades to reach the nearest stars. Decades of life support implies highly reliable closed-loop systems, large stores of food or sustainable production medical care over long periods, and the social stability of a small community in isolation. These constraints go beyond those faced by a Mars mission. They require a level of autonomy and endurance that has not been demonstrated. The communication delay would also remove Earth's practical support. Even at Proxima Centauri, messages take years. The crew would be independent. In human time, the mission would be closer to a long voyage across generations than to a mission with constant contact. The presence of these limits does not change the central point that the largest barrier is speed. Before addressing life support and shielding, the vehicle must first reach the required velocity. Current spacecraft velocities produce travel times of tens of thousands of years to the nearest stars, which is effectively unreachable in human terms. To reduce travel to decades, a new propulsion regime is required. Concepts that are often discussed include propulsion, driven by external energy, such as laser sails, where a vehicle is pushed by light from a distant source, and fusion-based propulsion, where nuclear reactions provide high energy density. These concepts illustrate possible directions, but are not operational realities for crewed travel. The script does not adopt them as given. It uses them as examples of what would be required in principle: far higher exhaust velocities, far higher energy density, and the ability to accelerate a vehicle to a significant fraction of light speed. Without such capabilities, human travel between star systems remains outside practical reach. This is the measured limit. The nearest stars are only a few light years away, yet they are separated by a gulf of time when travel speeds are low. In the solar system, a decade can reach Pluto. A few decades can reach the heliopause. Beyond that, a few light years require tens of thousands of years at current speeds. This step change is why the light year is a boundary concept. It marks where human travel with current propulsion stops being a project and becomes an era. The next step is to discuss relativity and the speed ceiling more directly, because once travel times are reduced toward decades by higher speeds, the nature of time, energy, and causality becomes relevant. Relativity does not create an escape from the speed of light as a limit, but it defines how motion and time behave as speeds increase, and why faster than light travel is not part of known physics for moving objects. This will clarify the ceiling that remains even if propulsion improves dramatically. Once distance is measured in light years, the speed of light becomes more than a communication limit. It becomes the central ceiling that shapes what travel can mean at all. The outer region here is relativity and the speed ceiling, because it defines how motion behaves as speeds increase, and why faster-than-light travel is not available in known physics for objects that carry mass and information. Relativity begins with a simple empirical fact. The speed of light in vacuum is the same for all observers regardless of their motion. This is not an assumption of convenience. It is supported by experiment and underlies modern physics. From this, several consequences follow. One is that as an object accelerates to higher speeds, adding energy continues to increase its momentum, but the speed approaches the speed of light asymptotically and does not cross it. Another is that time and space measurements depend on relative motion. A clock moving at high speed relative to an observer runs slower, as measured by that observer. Lengths along the direction of a motion are measured as contracted. These effects are small at everyday speeds, but become important at a significant fraction of the speed of light. In human time, these effects matter because they define what a decades-long interstellar trip at a fraction of light speed would mean both for observers on Earth and for travellers on board. Yet the more immediate relevance to limits is the speed ceiling itself. If objects cannot exceed the speed of light, then travel between stars cannot be made arbitrarily quick. Even if a vehicle could travel at 90% of light speed, a journey to a star 4 light-years away would still take more than 4 years as measured from Earth, and more when acceleration and deceleration are included. The ceiling therefore sets a lower bound on travel time as measured in the departure frame. It is not possible to make a 4 light-year trip take a few months as measured from Earth without faster-than-light travel. Relativity enforces this by the structure of space-time. The next question is whether time dilation could make the trip shorter for the travellers. Time dilation does mean that travellers moving at high speed experience less proper time than Earth experiences. If a vehicle travels at a very high fraction of light speed, the travellers' clocks advance more slowly relative to Earth's clocks. This could make the experienced travel time on board shorter than the time that passes on Earth. For example, at speeds close to light speed, the time dilation factor becomes large, and the onboard duration could be reduced. However, reaching such speeds requires enormous energy, and the Earth frame travel time remains constrained by distance divided by speed. Time dilation does not allow the vehicle to arrive sooner in Earth time. It changes the relationship between Earth time and onboard time. In human terms, this means that even in a future where near light speed travel were possible, the travellers might experience a shorter trip than the people left behind, but Earth would still wait for years for a nearby star, and for decades or longer for farther ones. This creates a different kind of human limit, the separation between the traveller's lived time and the homeworld's time. It would be a one-way desynchronization because the travellers would return to a future Earth. This is not presented as meaning or drama here. It is a physical consequence of relativistic motion. The ceiling also interacts with energy requirements. As speed increases toward the speed of light, the energy needed to add further speed grows rapidly. In classical mechanics, kinetic energy grows with the square of speed. In relativity, the energy growth becomes even steeper as the speed approaches the limit because the relativistic factor increases without bound. This means that pushing a vehicle from 90% of light speed to 99% requires a large additional energy increase. The closer one tries to get to the speed of light, the more energy is required per incremental gain in speed. This makes the last portion of the approach extremely costly. For interstellar travel, this implies that there is a practical optimum below the extreme end. Even if high-speed travel were possible, the energy and shielding costs might make it impractical to attempt to get extremely close to light speed. Thus, the speed ceiling is not only absolute, it also creates a steep gradient of difficulty that intensifies near the limit. Another aspect of relativity relevant to travel limits is causality, the ordering of cause and effect. In the relativistic framework, faster-than-light signals can lead to situations where different observers disagree about the order of events, and where cause-effect relationships can be violated in certain frames. This is one of the reasons faster-than-light communication and travel are not part of standard physics. The speed of light is not simply a technical speed limit. It is tied to the structure of space-time and the preservation of causal order. This script does not attempt to prove this formally. It states it as the accepted framework within known physics information, and objects do not travel faster than light in vacuum. This sets the operational boundary for both travel and communication. Concepts that propose bending space-time, such as hypothetical warp drives or wormholes, are sometimes discussed in theoretical contexts, but they require conditions such as exotic energy densities that are not known to be physically realizable. They remain speculative and are not part of demonstrated engineering. Therefore, within the scope of scientific consensus, the speed ceiling remains. It defines the ultimate limit on how quickly worlds can be reached when those worlds are separated by light years. Relativity also affects how hazards scale with speed. As a vehicle moves through interstellar space at relativistic speeds, even low-density gas becomes a hazard because relative particle energies become high. The vehicle would encounter hydrogen atoms and dust grains at high relative energy. Collisions would produce radiation and heating. Shielding would need to be designed for this. The faster the vehicle, the more severe the hazard. This creates a second practical ceiling in addition to the energy ceiling. Even if energy were available, the environment might impose a limit on safe speed. This is not an absolute limit like the speed of light, but it is a physical constraint that becomes stronger as speed increases. For human travel, it would mean that speed increases must be balanced against the mass and complexity of shielding, and against the risk of radiation exposure produced by impacts. Again, mass feeds back into energy. This is a recurring pattern in travel limits. Solving one problem worsens another. Relativity also frames the question of acceleration. To reach a significant fraction of light speed, a vehicle must accelerate for long periods unless the acceleration is extremely high. High acceleration can be dangerous for humans and can demand enormous thrust. Lower acceleration is more comfortable but requires long acceleration time and long distance. A vehicle accelerating gently could take months or years to reach high speed. It would then need to decelerate similarly to arrive at a star system at a manageable speed. This means that even if a vehicle could reach high cruise speed, the total trip time includes long phases of acceleration and braking. These phases use energy and add to the timeline. In human time, this matters because a journey that appears to be a straight cruise at high speed might actually be a long period of gradual change. It also affects onboard gravity if acceleration is used as artificial gravity. A constant acceleration could provide a gravity-like force for the crew, which could mitigate microgravity effects. But maintaining such acceleration requires continuous thrust and power. Again, the energy requirement becomes central. Thus, relativity does not only tell a story about time dilation, it defines a network of constraints around speed, absolute ceiling, steep energy growth near the ceiling, environmental hazards that scale with relative velocity and practical acceleration requirements. Together they explain why even with advanced propulsion, the distance between star systems remains a serious time challenge. The nearest stars might be reachable in decades in Earth time if high fractional light speed were achieved, but this would require energy systems and shielding far beyond current capabilities. Farther stars would require longer times and would face the same ceilings. Within this framework, faster-than-light travel is not available, so travel times cannot be reduced below the light travel time as measured from Earth. The speed ceiling therefore defines the ultimate outer boundary of human travel speed. It does not say humans cannot travel far. It says that distance will always translate into time in a way that cannot be removed by engineering once the scale is measured in light years. The next step is to examine what this implies for missions that extend beyond a single human lifetime, such as generation-scale travel. Without relying on speculation, the focus will remain on the operational burdens implied by multi-century travel life support over generation social stability and the management of a vehicle as a long-lived habitat. This will show how when travel times exceed lifetimes, the limits of human travel shift from propulsion and physics to continuity and endurance. If travel times exceed a human lifetime, the limit of human travel changes character. The question is no longer only how to propel a vehicle across distance. It becomes how to sustain a human community and its life-supporting machinery across decades, centuries, or longer without external resupply or rescue. The outer region here is generation-scale travel as an operational burden, because it describes what multi-century durations imply even before any destination details are considered. This is not presented as a plan or a promise. It is a calm accounting of what would be required if travel time remains long. The first requirement is continuity of life support. For months-long missions, closed-loop recycling of air and water can reduce consumable mass, but food still largely comes from stored supplies. For multi-decade or multi-century missions, stored food is not practical as the primary source, because the mass would be enormous and the storage would have to remain safe and edible for extremely long periods. This implies some form of ongoing food production within the vehicle. Food production requires water, nutrients, energy, and controlled environments. It also requires stability against disease and system failures. A long-duration vehicle would therefore need to function as a habitat not only as a transport. Air would need to be recycled continuously. Carbon dioxide would need to be removed and managed. Oxygen would need to be generated. Water would need to be recycled with very high efficiency. Waste would need to be processed into usable nutrients. These requirements are already challenging in small form for space stations. Scaling them into a system that operates for generations without outside parts would require extreme reliability and maintainability. Every subsystem would need redundancy and the ability to be repaired using onboard resources. This leads to the second requirement: maintenance and manufacturing capability. Over decades and centuries, components fail. Materials fatigue, electronics degrade, seals leak, pumps wear, filters clog. Even if the initial build is robust, failure is unavoidable on long time scales. Therefore, a generation ship concept implies onboard fabrication and repair. This is not limited to making simple parts. It would require the ability to manufacture complex components, including electronic sensors and structural elements using raw materials available on board. Those raw materials could be carried from Earth or obtained from resources encountered, but in interstellar space there are no convenient stops for mining. Carrying raw materials adds mass. The manufacturing system adds mass. It also adds energy requirements and complexity. Yet without it, a long voyage would be limited by the lifetime of its parts. This is a fundamental durability limit. The third requirement is population and social stability. A multi-century voyage implies multiple generations living and dying on board. A stable population requires enough people to maintain genetic diversity and to support a functional society with specialized skills. Too few people could lead to inbreeding and loss of capability. Too many people would require more resources and larger habitat volume. The habitat would need to provide living space, work space, medical space, and psychological relief. It would need governance structures that remain stable over time. It would need education systems to train new generations to operate and repair the ship. Knowledge must be preserved accurately across centuries. This is not automatic. It requires institutions and records that survive disruptions. The ship's community would need to maintain motivation and cooperation for a purpose that individuals may not personally complete. This is not discussed as meaning. It is discussed as continuity of mission function. Without stable social organization, the technical systems would not be maintained. Thus, social stability becomes a travel limit. The fourth requirement is health in long confinement. Even if food and air are provided, long-term confinement can affect mental health, physical health, and social dynamics. A habitat would need to manage stress, conflict, and long-term well-being. It would also need to manage reproduction, childcare, and aging. Medical care would need to handle not only emergencies, but the full spectrum of human health across lifetimes. That includes surgery, infectious disease management, chronic conditions, and childbirth. A habitat would need medical equipment and the ability to maintain it. It would need pharmaceuticals and the ability to produce or synthesize them over long-time scales, because stored medications degrade. This introduces another manufacturing requirement. The fifth requirement is radiation protection over long periods. A generation-scale voyage would expose the habitat to cosmic rays continuously. Shielding can reduce dose, but shielding mass is heavy. One approach is to surround the habitat with large mass such as water or other materials, which can serve as both resource and protection. Over centuries, the cumulative dose must remain within survivable limits, which suggests that shielding must be substantial and consistent. Active shielding concepts exist in theory, such as magnetic fields, but these require power and complex engineering and have not been demonstrated at the scale needed. Therefore, practical discussions often return to mass shielding, which increases the vehicle's mass and makes propulsion harder. This again links endurance constraints to propulsion constraints. The sixth requirement is propulsion and navigation reliability. A generation voyage cannot rely on short, intense burn alone if it needs to accelerate and decelerate over long distances. If the vehicle uses a propulsion system that must operate for years or decades, that system must remain reliable for that duration and must be maintainable. If it uses a propulsion system that provides a one-time push and then coasts for centuries, then navigation must remain stable, and course corrections must be possible with the limited propellant on board. Over centuries, small errors can accumulate into large missed distances. The vehicle must track its position and velocity relative to the destination and must adjust. This requires sensors computation and the ability to perform maneuvers. Communication with Earth would not be useful for navigation because of years-long delays. The ship must be self-navigating. It must maintain star tracking systems and maintain the knowledge needed to interpret them. It must also maintain protection against micrometeoroids and dust. Over light-year distances, even at modest speeds, the number of potential impacts accumulates. Shielding, repair, and redundancy become essential. The seventh requirement is the control of environment and ecology. A habitat is a closed system in which air, water, and biological processes are linked. Closed systems can become unstable. Small imbalances in nutrients or microbial populations can grow. Disease can spread. A sustainable habitat would need careful management of microbiology, agriculture, and waste processing. It would need monitoring systems and the ability to respond to changes. This is a complex engineering and biological problem. It is a limit because small failures can cascade over long durations. Earth's biosphere is stable in part because it is vast and has many buffers. A ship habitat would be small and tightly coupled. It would need engineered buffering and careful operation. The eighth requirement is purpose continuity without external enforcement. A spacecraft mission today is operated by a team with clear objectives and with external funding and oversight. A generation voyage would rely on the community on board to continue the mission across centuries. The mission's goals might remain known, but the incentives and priorities could change. This is not a moral statement. It is an operational risk. If the mission depends on maintaining a course and performing a controlled arrival, the community must continue to value and execute those tasks. Otherwise, the ship becomes a drifting habitat without a defined endpoint. To avoid this, systems would need to be designed to make mission continuation robust to social change. That is a design challenge in governance and in technical automation. It implies higher autonomy in navigation and safety, perhaps reducing the reliance on collective decision for essential functions. But autonomy itself introduces risks if systems fail. Thus, the limit remains one of coupled complexity. In human time, multi-century travel is not simply waiting longer. It is sustaining a civilization-scale system in miniature. It requires power generation for centuries maintenance and manufacturing, for centuries stable social institutions for centuries, and medical and ecological stability for centuries. These requirements are far beyond current practice. They are not forbidden by physics in the same way faster-than-light travel is, but they are bounded by complexity and reliability. They show that if propulsion does not reduce interstellar travel to within decades, then human travel becomes an endurance project on a scale that resembles settlement more than voyage. This is why generation travel is often described as a different category of mission, not simply a longer one. It changes the central problem from propulsion to sustainability. The script does not claim that such a system will be built. It states what the timescale implies. It is the direct translation of distance into the length of human lives and the durability of engineered systems. The next step is to move outward again from the ship to the larger structure of space describing horizons and unreachable regions. Even if a civilization could sustain long voyages, the universe contains limits defined by expansion and by the finite speed of light that place some regions permanently outside reach. This will show that the limits of travel are not only technological and biological, they are also cosmological. Beyond the limit set by propulsion biology and the speed of light for local travel, there is a broader limit that comes from the structure and evolution of the universe itself. The outer region here is horizons and unreachable regions, because at the larger scales some places are not merely far, they are separated in a way that cannot be overcome even in principle within known cosmology, since the universe is expanding, and the ability of signals and travellers to connect regions is constrained by that expansion and by the speed of light. This does not remove the reality of nearby travel within the solar system, or even within the local stellar neighbourhood. It adds a final outer boundary that frames what distance can mean when the scale grows from light years to billions of light years. The universe expands, meaning that on very large scales galaxies are on average moving away from one another as space itself stretches. This expansion is not like an explosion from a central point. It is a uniform stretching described by general relativity. A key observable consequence is Hubble's law, where the recession velocity of distant galaxies increases with their distance. For relatively nearby galaxies, the recession speed is small compared with the speed of light. For extremely distant galaxies, the recession can be very large. This does not mean that galaxies locally move through space faster than light in the usual sense. It means that the space between us and them increases due to expansion. In this framework, the speed of light remains the local speed limit for objects and signals moving through space-time, but the distance between far regions can still increase over time, faster than light could cross it because the metric distance grows. This is the foundation of cosmic horizons. A horizon in cosmology is a boundary beyond which events cannot influence an observer, because light from those events cannot reach the observer within the age of the universe, or cannot reach at all due to ongoing expansion. There are different horizons depending on the definition. One is the particle horizon, which defines the maximum distance from which light has had time to reach us since the beginning of the universe. This is related to the size of the observable universe. Light from beyond this horizon has not had time to arrive yet. Another is the event horizon, which defines a boundary such that events beyond it will never be able to affect us even given infinite future time, because the expansion carries them away too quickly. The existence and size of these horizons depend on the expansion history of the universe, including the effect of dark energy, the component associated with accelerated expansion. Observations indicate that the expansion of the universe is currently accelerating, which implies that there is a cosmic event horizon regions of space from which light emitted now will never reach us in the far future. This sets a deep limit on reachability. Even if a civilization could travel at nearly the speed of the light, it could not reach galaxies beyond the event horizon, in the sense of exchanging signals or travelling there and later interacting with the origin. The expanding universe would separate them causally. In human time, this horizon is not expressed in years or centuries, but in the structure of what can ever be connected. Yet it still links back to the idea of distance measured in time, the time for light to cross compared with the time over which the universe expands. The observable universe already shows this effect. Light from very distant galaxies reaches us today, even though those galaxies are now much farther away than the naive light travel distance would suggest. This is because the universe has expanded during the time the light has been in transit. The light does not travel through static space. It travels through expanding space. As a result, the distance to those galaxies today can be much larger than the number of light years light has been travelling. The correct description uses co-moving distance and the expansion history. In practical terms, this means that when astronomers observe galaxies at high redshift, they are seeing light emitted billions of years ago from regions that are now extremely distant. Some of those galaxies may now be receding from us at an effective rate greater than the speed of light due to expansion. This does not violate relativity because it is not local motion through space. It is the stretching of space between us and them. The relevance to travel is that reaching such regions would require crossing a distance that is not fixed. It grows. If the growth rate outpaces the traveller's progress, the traveller never arrives. Even for regions that are within the current observable universe, some are beyond the event horizon, and are therefore causally disconnected in the long term. This means that the universe contains regions we can see but cannot ever reach or communicate with in the future, depending on the details of cosmological parameters. In calm terms, seeing is not the same as reaching. The distinction between observable and reachable becomes important. A signal emitted today from Earth can only reach a finite region of space, even in infinite future time if the universe continues accelerating. That region is the future-like cone of Earth. Its boundary defines what can ever be influenced by an event on Earth. Similarly, there is a finite region that can ever influence Earth in the future. Beyond that is the event horizon. For human travel, which would be at less than light speed, the reachable region is smaller still. A civilization could expand through nearby interstellar space, and perhaps through parts of the local group of galaxies over very long times, but the accelerating expansion implies that over enough time distant galaxy groups will disappear from causal contact. Local gravitationally bound structures remain bound and do not expand internally. The Milky Way and Andromeda, for example, are bound and are expected to interact and merge over time. The local group is a bound structure. Travel within such a bound region is limited by propulsion and biology, and the speed of light, but not by cosmic expansion in the same way. Beyond the bound region, expansion dominates and the horizon becomes relevant. This introduces a hierarchy of limits. On the smaller scale, travel is limited by engines and life support. On the interstellar scale, it is limited mainly by achievable fraction of light speed and by shielding. On the cosmic scale, it is limited by the expansion of space itself. Each scale has its own defining constraint. The horizon also has a time aspect that can be framed in human terms as an analogy of waiting and missing windows. In the solar system, launch windows open and close because planets move. On the cosmic scale, windows also close because regions move out of causal contact. Over extremely long times, accelerated expansion would make more and more of the universe inaccessible, not because it becomes hidden, but because light and travel cannot bridge the growing gap. This is not presented as destiny or meaning. It is a statement of the current standard cosmological model. The magnitude is beyond daily experience, but the structure is familiar motion, and timing create limits. Another cosmological limit is the finite age of the universe. The observable horizon exists because the universe has had a finite time since its early hot dense state. Light has only had so long to travel. This means there are regions from which light has not yet arrived. If the universe had existed forever in a static state, the observable universe would be infinite. It is not. Its finiteness in terms of what can be observed is a time limit. For travel, this implies that even with near-light speed travel, a traveller cannot reach beyond where information could ever arrive because there is no causal connection established. Yet travel itself establishes a causal connection through the traveller's world line. The deeper point is that causality in relativity defines what is possible. Travel and communication are forms of causal influence. Cosmic horizons define the ultimate boundaries of causal influence. They are therefore the ultimate boundaries of travel and communication. Within the limits of scientific consensus, these boundaries are not negotiable. They depend on the universe's expansion parameters. The script does not attempt to compute them. It states the qualitative result. The accelerating expansion implies a finite region of the universe that can ever be reached or influenced. This does not diminish the scale and richness of travel within the reachable region. It clarifies that distance between worlds does not only grow, it can become absolute in the sense of causal disconnection at the larger scales. This section therefore sets the outermost boundary in the outer to inner path. After placing that boundary, the final section can return inward one step to summarize the measured limits across scales in a quiet factual way. Seconds to the Moon, minutes to Mars, hours to the outer planets, decades to the heliopause, thousands of years at current speeds to the nearest stars and the cosmological horizons that define a finite reachable universe. This summary will remain descriptive, not interpretive, and will end by holding the scale steady rather than drawing meaning from it. The distance between worlds becomes a limit on human travel when it is translated into time and into the resources required to survive that time. The scales discussed so far form a sequence that is consistent and measurable, moving from nearby seconds to far horizons, with each step adding constraints that do not cancel the earlier ones. The outer region of this final section is the measured ladder of limits across space, stated as facts that connect: distance, travel, duration, communication, delay, energy, and human endurance without adding interpretation. The first rung is the Earth-Moon system, where the distance is large by Earth standards, but small in solar terms. Travel time to the Moon is measured in days for spacecraft and can be supported by short mission architectures. Communication delay is measured in seconds. The round-trip delay is short enough that Earth support remains nearly immediate, and return is possible within days. The limiting factors in this region are mostly operational and engineering rather than endurance. A crew must survive vacuum radiation in space and the demands of launch and landing, but the short timeline limits cumulative exposure. This makes the Moon the most accessible world beyond Earth in human time. The next rung is the inner planets, where distances are measured in fractions to a few astronomical units and vary with orbital alignment. Here, communication delay grows into minutes. A signal to Mars can take minutes to arrive when Mars is closer, and can take more than 20 minutes when Mars is far. This shifts operations from interactive control to planned sequences and local autonomy. Travel time for efficient interplanetary transfers is measured in months. This duration introduces cumulative exposure to radiation beyond Earth's magnetic protection and prolonged time in microgravity during transit. Life support must be more robust. Resupply is not practical once the mission is underway. The definition of reachable changes from being a matter of speed to being a matter of sustaining systems and health for a long span. The orbital mechanics of launch windows and return windows become practical schedule limits. A crewed Mars mission becomes a mission of many months of travel, and often a long total duration when return alignment is included. This is the threshold where the limits of human travel become dominated by time-linked biological and logistical constraints. The next rung is the outer solar system, where distances are measured in many astronomical units, and where travel time for robotic missions is measured in years. Communication delay becomes tens of minutes to hours. At Saturn, the one-way light time is on the order of more than an hour depending on geometry. This forces a high degree of autonomy. It also makes emergency support from Earth slow, and makes physical rescue unrealistic. For humans, a journey to the outer planets would not only require years in transit each way, but would also demand life support, reliability, radiation protection, and psychological endurance across many years with no resupply and no rapid return. Even if propulsion could deliver the vehicle, the time in deep space would amplify health risks and mass requirements. Shielding adds mass. Mass increases propulsion demands. Attempting to reduce travel time by increasing energy increases departure energy needs and arrival speeds, which adds further burdens. These coupled constraints define why robotic missions can reach the outer planets routinely in years, while human travel remains concentrated closer to Earth. The next rung is the far boundary zone of the solar system, where the relevant distances grow to tens and then around 100 astronomical units. The Kuiper belt is reached by fast robotic missions in about a decade for certain targets, showing that even aggressive trajectories still require human-scale decades to reach the outer small-body populations. The heliosphere's outer boundary, including the termination shock and heliopause, is reached by the fastest probes over multiple decades. Communication delay at such distances becomes many hours one way, making supervision slow and making autonomy essential. In human time, decades are long enough to exceed the working life of many individuals and to require institutional continuity. For humans, decades in deep space would demand life support and health management beyond demonstrated practice. Return would double the time. The mission would become an intergenerational commitment even before it leaves the solar system. This is where the simple arithmetic of time becomes a hard boundary. The next rung is the nearest stars. Here, the light year becomes the relevant unit. A light year is a distance defined by a year of light travel. Proxima Centauri is a little more than 4 light years away, meaning light itself requires more than 4 years to cross. At current spacecraft speeds, which are tens of kilometers per second, travel times to the nearest stars are measured in tens of thousands of years. This places interstellar travel far outside human time as lived in individual lifetimes. To compress interstellar travel into decades would require speeds that are a substantial fraction of the speed of light, which would demand energy per unit mass millions of times, greater than that associated with current deep space flight speeds. Such speeds would also introduce extreme hazards from impacts with interstellar dust and gas, and would require heavy shielding and high reliability over long durations. Even if high-speed propulsion were achieved, relativity sets a ceiling. Objects carrying mass and information do not exceed the speed of light in vacuum within known physics. Time dilation can reduce the experienced time for travelers at very high speeds, but it does not make the trip shorter in Earth time than the distance divided by speed allows, and it introduces desynchronization between travelers and those left behind. The ceiling therefore sets an ultimate lower bound on travel time between star systems. The next rung is the cosmic scale, where horizons appear. The universe expands, and on the larger scales, expansion creates regions that cannot ever be reached or influenced if accelerated expansion continues as observed. These horizons are not technological limits. They are limits of causal connection set by the structure of space-time. They define a finite region of the universe that can ever exchange signals with a given location and a finite region that can ever be reached by any traveller limited by the speed of light. Local bound structures such as the local group of galaxies remain reachable in principle, given enough time and appropriate propulsion, but far beyond them, expansion places some regions permanently out of reach. This is the outermost statement of limit. It is not a limit of endurance or engineering. It is a limit of the universe's geometry and evolution. Across all rungs the same pattern appears. Distance becomes time in two ways. It becomes travel duration at speeds far below light speed shaped by orbits and energy. It becomes communication delay at the speed of light shaped only by separation and geometry. For human travel time then becomes exposure requiring radiation protection, microgravity mitigation, reliable life support, medical capability and social stability. Every mitigation adds mass. Every added mass increases the energy required to move. Attempts to reduce time by increasing speed increase energy demands and environmental hazards. Attempts to reduce energy demands by taking longer routes increase exposure and mission duration. These trade-offs are not imperfections in planning. They are the structure of travel between worlds under known physics. Measured in human time, the solar system remains a place where nearby worlds can be reached in days and months, and where distant regions require years and decades for robotic craft. Beyond the solar system, the gap to the stars requires either new propulsion that reaches a substantial fraction of light speed, or acceptance of travel times that exceed human history. At the largest scales, horizons set an ultimate boundary on reachability, regardless of propulsion. These are the limits as they stand when distance is translated into time, energy and endurance, without adding conclusions beyond the measurements themselves.